Hello and welcome to my talk. My name is Sebastian and I want to talk about galaxy cluster cosmology with a South Pole telescope and a dark energy survey. And obviously this work is in collaboration with the South Pole telescope and the dark energy survey collaborations. So in a nutshell, what I want to talk about is describing this plot where we look at omega matter and sigma 8, and in blue are our latest published constraints from Bocquet 2019. And the question is, how do we get from this to forecasted constraints from SPT-3G and LSST, as shown in red here. And obviously I want to describe intermediate steps on our way to get there. So this presentation is structured as follows. First, I want to give an introduction to cluster cosmology for those of you who are not too familiar with the concepts. Then I want to describe the status of the published SPT cluster cosmology results. And then I want to describe what we're working on currently in terms of an analysis of the SPT abundance with DES weak lensing measurements. And in the end, I'll wrap up with a summary. So cluster cosmology in a nutshell. I have a couple plots for you. So on the top left, you see a simulated volume of the universe simulated for different, rather extremely different cosmologies. So on the left, you see the standard model. The middle one is a model with no dark energy. And then on the right, you have warm dark matter. And you kind of see by eye that structures are quite different. And especially if you look at massive dark matter halos, which are the most brightest points in these panels, you see by eye that by looking at the abundance of such halos, you should be able to learn about the cosmological model. Another way of putting it a little more specifically is the plot on the top right, where you see two different rows. The top one is lambda CDM and the bottom one is a matter-only Einstein de Sitter universe. And these were chosen such that the rightmost panels show pretty much the same abundance of halos. But then as you look at higher redshifts, you see again by eye that in the lambda CDM model, you do see clusters at redshift 1 and beyond, whereas in the Einstein de Sitter universe, you would have no clusters at redshifts beyond 1. So here again, intuitively, that tells us that if we measure the halo abundance as a function of redshift, we should be able to learn about dark energy as well. Now, to get a little more quantitative, I have this plot on the bottom left for you, and I show you the increase in, or the change in the halo mass function, so the abundance of halos, when I change omega matter by 5%. And you see that the change in halo abundance is rather dramatic. So again, if we have a good measurement of the halo abundance, we should be able to learn about cosmological parameters rather precisely. But now, the main challenge that we have here is we're looking at simulations, so we know the masses of the halos, but in practice, obviously we don't, because all we have is observations of halos. So the key program in cluster cosmology is basically to reconcile the halo mass function, which is the theoretical prediction. So that's the quantity on the left here. As I said, this is exponentially sensitive to cosmology. It's obtained from numerical simulations, and we know it rather accurately. And we need to confront this to measurements, which are on the right here in this slide. So basically, for each cluster, we have pairs of measurements, or observables in redshift. So the way we link this is the equation in the middle, and it's basically just converting the halo mass function from mass space to observable space. So two elements enter here. One is the observable mass relation, and I'm going to be talking about this quite a lot in this talk. And then the volume element that depends on the expansion history. So for the observable mass relations, the gold standard these days is to do mass calibration using weak lensing data. Now, why is that? This is because lensing traces the total mass. We do not need to assume anything about hydrostatic state of the clusters. And we do have accurate predictions and modeling from numerical simulations. And I'm going to come back to that toward the end of the talk. Now for this talk, I'm describing cosmology with clusters from the South Pole telescope. So there it is. It's a 10-meter telescope very close to the South Pole. It's observing in 3mm wave bands. And you see that now we're in the third survey, SPT-3G, but most of this talk is actually describing SPT-SZ and SPTpol. So with such millimeter wave data, we can observe clusters via the Sunyaev-Zeldovich effect, which I'll call SZ effect throughout the talk. And the picture is the following: as photons from the CMB pass through the hot gas of clusters, the spectrum gets, the CMB blackbody spectrum gets shifted to higher frequencies. And then as you see in the right panel here, the change in the spectrum has this characteristic shape. And in blue, I've indicated roughly where the 3 SPT bands are. So basically for SPT, clusters look like darker spots in the CMB. And the important point is the SZ effect is independent of redshift, so we detect clusters out to the highest redshifts where they exist. Now let's look at the sample. On the left here, I show the cluster sample and redshift and estimated mass space, and black crosses are all SPT-SZ clusters. So precursor analyses that use these samples are Benson et al., Reichert et al., Bocquet et al. 2015, and Dehaene et al. And this full SPT-SZ selected cluster sample has 343 clusters above redshift of 0.25 and a Z detection significance of 5. We then acquired follow-up data, so for X-ray from McDonald et al., which are the blue highlighted plots here. And then we have weak lensing data from HST and MegaCam highlighted in orange and green, respectively. Now, how do we put this together in an analysis? This is the main analysis strategy. So on the left-hand side here, I show you the likelihood function. Then I'm splitting in 2 colors here for reference. So the blue part is what I call the abundance likelihood. So this is basically treating the abundance of halos, so the distribution of clusters in SZ signal in redshift space. And in practice, we're assuming a Poisson likelihood because sample variance is negligible for the SPT sample. And then the green likelihood is the mass calibration part. So it's basically treating the measurement of follow-up observables from weak lensing and X-ray. And then the key point really is that we use the known M weak lensing to M halo relation to calibrate the SZ to mass relation. And that's what this plot here is showing. On the x-axis, we have the weak lensing inferred mass, and on the y-axis, the SZ signal. And then in red, we have our best fit model, and that's from Dietrich et al. 2019. So with this, we can now do cosmology, but in practice, of course, we sample the abundance and the mass calibration likelihood at the same time to do a simultaneous analysis to account for all parameter covariances. So this is our result that I showed in the beginning. Again, blue is our SPT clusters. This is for a lambda CDM model with massive neutrinos. And the important point is that for the SZ scaling relation parameters, we adopted wide flat priors. So all the mass calibration information really comes from the weak lensing follow-up data. So this measurement is limited by the number of clusters we have in the sample, and more specifically, the number of weak lensing clusters, because this sample only has 32 clusters with weak lensing data, and yet we're able to provide rather interesting constraints. Another thing I want to draw your attention to is the plot on the bottom left. Here we're showing the abundance of SPT clusters as a function of redshift and SPT detection significance. And so the histograms are the data, and then the green lines are the model prediction from our best fit model. And so you see that things are working out rather nicely. There's no sign that anything goes terribly wrong. And that gives us confidence for the next steps, which I'm going to describe in the following. So how do we improve over this result? As I said, there are 2 obvious step forwards. One is to use a larger cluster sample to reduce the statistical uncertainties, and we add more weak lensing data. So first, I want to highlight 2 recent analyses in this direction. So first, on the left-hand side, we have new SPT cluster catalogs. So the first was presented in Huang et al. 2020. That's using the deep 100 square degree SPTpol survey. And in this plot, these are the clusters with the green triangles. And you see we're pushing to lower halo masses and high redshifts. And the second is the wide 2700 square degree SPTpol extended cluster survey as presented in Beam et al. 2020. So when we combine all the SPT cluster samples, we have about 1,000 clusters above detection significance of 4.5. And at this point, most of the redshifts and optical confirmations come from the dark energy survey. I'm going to come back to that. On the right-hand side, I show recent progress on the lensing, weak lensing front. So this is a new analysis using HST for cluster weak lensing. And so basically in this work led by Tim Schrabak, we are increasing the HST sample from 13 clusters that I've described so far and increase it to 30 clusters with HST weak lensing. And so with this data, we're now able to really start to probe the evolution of the SZ signal as a function of redshift. And so you see here with the data points that we're now able to constrain the evolution between redshift of 0.25 and redshift of about 1.1 using weak lensing. And so this will become really important as we're trying to get better constraints on dark energy. Now let's switch gears and talk a little bit about synergies with the dark energy survey. So I suppose, as most of you know, the dark energy survey was conducted at the CTIO Blanco telescope. It covers 5,000 square degrees and 5 broadband filters. At this point, the survey is complete, and the collaboration is mainly focusing on analyzing year 3 data. And as you've certainly seen, there was the big data release of the 3x2 point cosmology analysis a couple of weeks ago. What's important for this talk is that the DES survey overlaps the SPT footprint, as is shown in this plot here. So the green outlined contours are the dark energy survey, and then the other colors are the various SPT surveys, and you see that there's a very good overlap, of course, and that's by design. So what we're currently working on, and what I'm specifically working on, is a paper series of SPT clusters with DS and HST weak lensing. So this work is mainly done in collaboration with Sebastian Grandes, Matthias Klein, Joe Moore, Tim Schrabak, and of course, many folks in the Dark Energy Survey and SPT collaborations. So we expect first papers to be out by the end of this year, so fingers crossed. So in the following, I just want to highlight a couple of analysis building blocks that will go into this analysis. So let's start with the data side. So there are 3 important aspects to the weak lensing of clusters that I want to highlight here. So let's go left to right. So on the left-hand side here, I show the impact of cluster member contamination, which you might also refer to as boost factors. So the idea is that cluster members can scatter into the sample of source galaxies and therefore dilute your weak lensing signal. So you need to account for that. What we do is we use the so-called PFZ decomposition method that's been used by a lot of previous analyses. So in this plot here, this is borrowed from Paulus et al., which is going to be submitted in a very short time. So Maria used DS year 1 data to look at the cluster member contamination, and in the plot on the left, you see the impact of cluster member contamination as a function of cluster-centric radius for a couple of cluster redshifts. Okay, let's keep moving. Let's look at miscentering in the center column. Miscentering is important because in practice, we only have observational halo centers. And if you measure the shear profile around these positions, you have a miscentered profile with respect to the true halo center. So we do a 2-step analysis to account for that. So in the top plot here, I show the off-centering in the Magneticum hydro simulation. The data was processed by Lindsay Bleem. So the green histogram is the simulated data, and then in colored, especially in orange, we have our model that's able to reproduce the data. And in the second step, we look at the miscentering between SZ centers and optical centers. And again, we have the data this time in blue, and then the model in orange, which indicates a good fit. So with this, we're now confident to actually extract weak lensing data for SPT clusters, and that's what this plot here on the right shows you. That's the tangential shear as a function of radius. This is for all SPT clusters above signal to noise of 4.5, and using this radial range as indicated. And the total signal to noise in this measurement is around 80. So you really have a lot of signal. So now let's discuss systematics a little bit. So for this analysis, we used the same tomographic source selection as the DSY3 analysis, the 3x2 point analysis using DSY3. And so on the left-hand side here, you see the lensing efficiencies for each tomographic bin as a function of cluster redshift. And we weight each tomographic bins by this lensing efficiency to combine the different bins. In the bottom row, I show the systematic uncertainties in inverse sigma crit, which is basically the product of the impact of shear calibration and photo Z calibration. And you see that DS is able to provide this to a % level up to a redshift of about 0.5 or so. And this is a significant improvement over DS year 1, which is highlighted as the purple line here. So the last ingredient before we can do a cluster cosmology analysis is the so-called weak lensing mass model. So the idea is the following. As you all know, real halos are messy. The approach we use in fitting is that we fit something like an NFW-inspired shear profile to the data. Obviously, as halos are not NFWs, there is a resulting mass bias and scatter in what we call the M weak lensing to M halo relation, and this has been recognized in a lot of the existing literature. So we followed this approach, and a recent paper led by Sebastian Bocquet put this a little bit further to also include other systematics in this M weak lensing to M halo relation, notably the effects I just described, miscentering, boost vectors, source photo Z, shear calibration, uncorrelated loss structure. So we fold all of that into our model. As I said, we restrict our weak lensing analysis to the one halo term regime. The reason is the following. We want to exclude the innermost part of the halo where miscentering is important and where the cluster core might be doing its thing. And we exclude the two halo term regime because this makes the modeling a lot more complicated. We then use hydrodynamic simulations to calibrate the relationship between the gravity-only halo mass and the weak lensing shear profiles. This has a number of advantages. First, this allows us to use the most precise halo mass function predictions that come from emulators, and these are so far based on gravity-only n-body simulations. And second, we compare these results to the ones we obtain when we use illustrious TNG instead of magneticum. And indeed, we find a 2% systematic in weak lensing mass between these two hydro simulations, and we fold these 2% into our systematics error budget. So we are then fully accounting for the impact of hydrodynamic effects on weak lensing shear profiles. So when we apply this machinery to DS year 3 data, we have a systematic uncertainty in weak lensing that's between 3 and 6% as a function of cluster redshift. So with this, we're now close to being able to do the analysis. At this point, where we are is we have validated the code against mocks. So I show one example on this slide. When red, you see the latest published result that I described, and in blue is then a realistic mock analysis, and we see that we're able to improve our constraints by quite a bit. And so the way the analysis is going to be done, it will be done blinded at the parameter level. So we want to be safe against confirmation bias. And while everything I show in this talk is rather preliminary, we hope to be able to start blinded data runs very soon. So with this, let me wrap up. The main takeaway, I think, is that we have a clear path forward for improved cosmology from SPT selected clusters. DS year 3 data will play a crucial role, and so stay tuned for the results, and I look forward to your comments and questions. Thank you.